In today's lesson, we'll be working with mathematical models. For mathematical models, you will be constructing and analyzing functions based on information that is given. We have two examples to go through today, and then in your practice, you'll try some more. Let's look at example 1. In example 1, it says we have a rectangle that has one corner on the graph of y equals 16 minus x squared, another on the origin, a third on the positive y-axis, and a fourth on the positive x-axis. In order to effectively solve these problems, it's a lot easier to visualize it. So drawing a picture of what this looks like can really help you to solve this type of problem. So let's think about what we have first. We have a rectangle, and we know that one of the corners lies on the positive y-axis, so vertically, and another corner on the positive x-axis. So it's going to sit in quadrant 1. We have a third corner that sits on a function, y equals 16 minus x squared. Now, picture what that looks like. Look back in your library of functions if you need to, but that's a squared function. And there's a negative in front of our squared x. So that means it opens down. And part of our rectangle intercepts that function. So let's draw a picture of what that potentially looks like. Over here on the right, you can see our rectangle has one corner here where that red dot is on the y-axis, another corner here where this red dot is on the positive x-axis, and then the third corner is here on that function. And here's a representation of perhaps what y equals 16 minus x squared would look like. So for part A, we want to express the area of the rectangle as a function of x. So that means we want to have this as A x. So our independent variable is x, and our dependent variable is a. We don't want any other variables in there. So how are we going to get to this point? Well, let's examine what we know. First of all, we're dealing with area. So what is our equation for area? Well, we know that area is equal to base times height. If I look at this rectangle, what is the value of my base? Well, in these mathematical models, you may not be given a value necessarily, but we do know that the distance from the origin out to this point is going to be x. So we can say that our area is equal to x. And then what about our height? Well, our height is a distance of y. So our area is equal to x times y. But that's still not expressed as a function of x. This is expressed as a function of x and y. So we need to get rid of the y. Well, if we look back at our problem, y is explained to us. Y is defined as 16 minus x squared. So we can substitute 16 minus x squared in for y in our area function. Again, using the substitution property, we're able to compose these functions together. So let's see what that looks like. We would have a as a function of x is equal to x times 16 minus x squared. So we do have now area expressed as a function of x, but let's go ahead and simplify this a little bit. So let's distribute our x term. We would end up with 16x minus x cubed. So now we know we have a cubic function, and we can visualize what that looks like. Let's look at part B. What is the domain of A? So what is the domain of the area? In other words, given these parameters where y is defined, what potentially would be the length of our base in order to stay within this parameter? So what we want to do is graph this function. Here's a graph of our cubic function, and you can see that it is a negative function, and you can tell that it is cubic if you look at the characteristics. Now, what is the area that we're concerned with? Are we concerned with the entire function? No, we are only concerned with the positive area, because if we're looking at a real-life problem, having a negative base length doesn't make any sense. So we're really only concerned with the area between 0 here and 4 here. So our domain, our base length, can really only be up to 4, greater than 0 and up to 4. So greater than 0, what would that look like if we wrote it in interval notation? That would mean we would have a parentheses. Because at 0, remember we had 0 area, so that doesn't work. But can we have a base length of 4? Well, if you look back at our graph, remember that at 4 here our area is 0. So we actually cannot have a base of 4. It has to be less than 4. So again, we would need a parenthesis in order to describe that part of the domain. So whenever we're dealing with domain in a mathematical model, we have to think realistically, what numbers make sense for this problem? So now let's graph, which we did. Determine for what value of x a is the largest. Well, all we have to do is look here at our max, and we can determine that at 2.309, we have an area of 24.63. And here we've written it down. So we have our base length of 2.3 approximately gives us a max area of 24.63 units. Okay, let's try our second problem. In this problem, we have a 12-inch piece of wire, and it's to be cut into a square and a circle. What we want to do for A is find the total area of the square and the circle as a function of x. Once we have that, we can determine the domain of the area function as well as find the minimum value of x. So go ahead and pause the video and see what you can come up with. Remember, the first thing you want to do is make a visual of what is being stated. So here we have our 12-inch piece of wire. Once we cut it, we can fold those pieces into a square and a circle. Now, go back to what you know. We're working with area of a square and area of a circle. So let's write the area formulas. We know that the area of a square is going to be, again, base times height. However, in a square, all the sides are equal. So we would say that's x times x, or x squared. In a circle, we know that the area is equal to pi times r squared. Now let's think about this. We just said that the square is equal to x times x. So let's go ahead and label these sides as x, 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 and x. Every side will have the same length. So we basically have 4 x's. If we take this wire and we cut off a piece of it, so I'll just say right here, and we use this to build our square, well, how long is this piece? Again, we don't have any numbers necessarily to help us, but we do know that we can define it as 4 x's worth. So this piece is going to be x plus x plus x plus x, which gives us 4 x's. Well, what does that leave us? What's left for the circle? If we started with 12, we can subtract what we just used, 4x, and this is what we have left for the area of the circle. Well, how are we going to find the area of the circle? Because we don't know the radius of this length. But what we do know is that this wire that's left forms the distance around the circle. Just like 4x was the perimeter of the square, 12 minus 4x is the circumference, or the distance around the circle. So we need one more equation to help us, and that would be circumference. So circumference is equal to 2 pi r. And if you forget any of your geometric formulas, you can always Google them, and then you'll know them. Okay, so now we know that circumference is equal to 2 pi r, and we know circumference. So we can start building some equations. Let's start with our circle. We define circumference as 2 pi r, and we know that 2 pi r will equal the 12 minus 4x, because that's the circumference, the amount of material we have left for the circle. So that equals 2 pi r. Now remember our ultimate goal. We want to find the total area of the square and the circle as a function of x. Well, we already have the area as a function of x for our square, but we don't for the circle. Well, what we need to do is we need to find something to plug in here for our radius. Well, here's an equation here, and we need to solve for radius in order to substitute r in for r squared. In order to do that, we would just need to divide both sides by 2 pi. And then we can simplify a little bit. So these cancel. 2 goes into 12 6 times and goes into 4 2 times. So we would be left with 6 minus 2x over pi is equal to our radius. Now that we know this, we can substitute this into our area formula for our circle. When we do that, we get area equals pi, and then all of this, 6 minus 2x over pi squared. In order to get what we need, we just need to add the area of the square to the area of the circle. So our total combined area, this would be with our square plus our circle, will now be equal to x squared plus pi times 6 minus 2x divided by pi, and then everything squared. In order to help us graph this, we should probably simplify this a little bit more. So we have 1 pi here and we have 2 pi's here. We can cancel out this one into one of these. So we would be left with x squared plus, for our numerator, 6 minus 2x squared all over just 1 pi. We went from having 2 because it was pi squared to just 1. So now we can graph this function and we can determine what our domain is. So let's look at our function. Here's what it looks like graphically. So how in the world do we determine our domain? In order to do this, you'll need to think about it logically. We have a 12-inch piece of wire. We need to make a box and we need to make a circle. Well, what's the maximum side length of the box that we can use and use up the entire 12 inches? If you take 12 divided by 4, that gives you 3. So if each side length was 3 inches, we would use up the entire wire. So we need to be somewhere less than 3 and greater than 0. Writing this out, we would get 0 to 3. So that's the domain of the area function. It's hard to tell by looking at the graph, but sometimes we need to think back logically and think about what we have, the materials we have. How about the minimum value of x? If we go back to our graph, that's easy to find. Our minimum is 1.68. That's our minimum value of x. And that minimum will get us an area of a combined area, I should say, of 5.04 inches squared. And that concludes our lesson today on mathematical models. So hopefully this was helpful. When you try them on your own, make sure to persist, to keep trying, and go back to the basics. Think about what you're finding and start with your basic formulas and see if you can use substitution and compositions in order to get where you need to go.